Let's consider our example that we considered when we introduced the non-holonomic constraint. Rolling without slipping. Very badly rolling, particularly on the board. Okay. So this is R and this is theta. These are X and Y. And this is the tangent. So this is the trajectory. This is the tangent. This is R theta dot. And this angle is phi. Okay? So this is a coin that is rolling without slipping on a surface. Okay? So we have 4 degrees of freedom. My configuration space is every x and y, and theta and phi. That is, xy is R2, theta is S1, phi is S1, right? Circles. Here is your manifold, configuration manifold, right? It's a curved space. That's okay. Well, not that much, but just again convincing you that we all the time we're living in curved spaces in mechanics. Okay, I have 4-dimensional manifold. 4-dimensional manifold. But it's subject to some constraints here, man. Why? Because it's rolling without slipping. Rolling without slipping dictates that the velocity coming from r theta dot is the same as the whole velocity of this point should be the whole velocity of the ground, which is 0, right? What's the whole velocity of this point? Well, there is a component coming from r theta dot. So r theta dot cosine and r theta dot sine. Cosine phi gives you y, sine phi gives you the x, and the negative x and y. So to get the whole thing, you need to add x and y here. You need to add x dot and y dot. This is the total velocity of the contact point, and it has to be 0. These are the 2 constraints that we wrote exactly before in that lecture. It's not our topic today to write these equations, but to deal with these equations. Any questions so far? So I have, the question now is that I have 4-dimensional manifold. I have a system of 4 degrees of freedom, subject to 2 constraints. So at each point, I am allowed only 2 free velocities, right? I cannot have 4 free velocities, 4 independent velocities. If I am, then I can cover the whole Q, of course. But at each point in Q, in my configuration manifold, at each position, at each attitude here, at each time, I'm allowed only 2 free velocities. Okay? The other 2 velocities are dictated because of these 2 constraints. Correct? Okay. The question is, despite the fact that you have 2 constraints, or can you use these 2 constraints to eliminate 2 of the degrees of freedom so that you are living on a reduced dimensional space? Okay? So let's write our system in a form that we can understand this language. And this is very easy, by the way. Here is the set of all velocities of my system. I have 4 degrees of freedom in general, x, y, theta, and phi. Okay? D by dt for them. These are all the sets of all velocities on Q. At any point, this is the tangent space of Q. This is equal to. Well, if they are all free, I'm done. But they are not all free. I only have 2 free. Why? Because I have 2 constraints. So, I will write the 4 velocities the two free velocities. Assume any of the velocities x dot, y dot, theta dot, phi dot. Assume any two of them to be free. It's up to you. Assume any two of them. Maybe theta dot and phi dot. Okay? So d by dt for theta dot is 1 times theta dot and 0 times phi dot. And the same here. D by dt for phi dot is 1 times phi dot and 0 times theta dot. But the other ones, x dot and y dot, now they depend on theta dot and phi dot in general. How you can fill these two? From the two equations. X dot equals what? R theta dot times sine phi. So this is R sine phi and 0 here. The other one is R cosine phi and 0 here. Before proceeding further, anybody has a question with this equation? If I give you two constraints like this, or you got them, and you want to check whether they are integrable holonomic constraints or they are non-integrable holonomic constraints. We're going to do a procedure to do that. The first step is to write them in this form. Any question about that? Yes, Joseph?
What's the surface that it's rolling on? Is it a straight line or is it?
In our case,
Yes.
here is the surface. You may not be able to visualize, but, and I don't care if it's visualized or not. It's a torus. This is a torus. This is the donut shape.
Oh, I mean the physical system. So it's a coin.
Oh, it's just a flat. It's a table. So this guy is rolling over a table. Rolling without slipping over a table.
Okay, I see. Okay.
Yeah. Any question about this equation? How do you write it? Any question? Okay, because the rest is very easy. What's the rest? Well, these are the only two admissible, these are the two allowed velocity vectors that I have, right? x1 and x2. These are the two vector fields that are allowed. And if I want to answer the following question, does there exist a surface such that these two guys are always tangent? The answer is easy, like we did over there. I'm going to collect them in a distribution, span of these two guys, and I'm going to check if this distribution is integrable or not. And how to check that? Thanks to Frobenius, the first thing to do is to compute what? Compute what? Lie bracket. x1 and x2. This is easy. It's partial x2, partial the states. Actually, x2 is constant, so this is 0. Minus partial x1, partial the, here is x1, partial all the coordinates. My coordinates are x, y, theta, and phi. We do the detail for you. Partial x1, partial coordinates times x2. This is negative. Here is x2 is easy. Let's do it together, please. Here is x1, and I'm going to differentiate it with respect to my coordinates, x, y, theta, and phi. The first element with respect to x, y, theta, and phi is r cosine phi. The second, no x, y, theta, and there is phi, so negative r sine phi. The third and fourth, they are actually constant, so when you differentiate, you get zeros. The result is what? Here is the result. Is r cosine phi negative r sine phi 0, 0. What do you want to check now? What do you want to check?
They are a new vector.
Say it again, please.
It's a linear combination.
Exactly. Is this guy is here or not?
It's there.
What do you think? Is it here or not? You can go and do all the tedious work to check if it's in the span or not, but you should be able to tell firsthand. Is this guy here or not? No, actually, and this I'll call this x3, okay? Actually, x3 is not only linear independent on x1 and x2, it's actually perpendicular to x1 and x2. If you do x3 dotted with x2, you get 0. do x3 dotted with this guy, you get 0. So it's actually perpendicular. If you want to make things very formal in writing, what we're going to do it, here's how we're going to do it. So x3, let's write it like this. x3 not in delta, meaning that delta is not what? Delta is not what?
Involutive.
Involutive, very good. Delta is not involutive. Involutive means the E bracket is in the set. Delta is not involutive, and if it's not involutive by Frobenius, you get what?
Not inverse.
We cannot.
Delta is not integrable. Delta is not integrable means that your constraint, you cannot integrate your constraint. This constraint, these two constraints, unlike this guy, which we can integrate, these two constraints cannot be integrated to eliminate 2 of the degrees of freedom. Okay? You will indeed be able to cover all the points in your configuration manifold using only 2 allowed velocities. Using only 2 allowed velocities, I will be able to cover all the configuration manifold. Okay? Any question about that? Last example. Yes, Joseph?
But here we only got 3 vectors, right, instead of 4. So where does the 4th one come from?
Where is the 3? I'm sorry. Where is the 3?
So you have x1, x2, and x3.
I don't have x3. X3 is the result of the Lie bracket in x1 and x2. I just called it x3.
But it's independent direction, right?
It's independent.